everyone. Today we'll be starting on a new topic called energy bands and semiconductors. In this topic we'll be learning about how to describe conduction in solids in terms of energy bands that electrons move between. So we'll be covering how semiconductors, conductors and insulators work in this manner. We'll start off with basic electron movement through solids and how electrons conduct electricity through metals and how they fail to through insulators. In this picture here we can see an extreme close-up of a number of iron atoms that was taken with a scanning tunneling microscope. The ripples in the middle represent what electrons would appear to look like. So to start off, conductors and insulators. Of course you've learned about these before. So different materials vary greatly in their ability to conduct electricity. This lets us classify materials as either conductors, like the bits of wire in this picture, or insulators, like the bits of rubber surrounding them. Now the conductivity of a material depends on its crystal structure. And this means that the crystal structure of semiconductors, conductors and insulators is quite different. Now insulators are materials that do not conduct electricity, no matter how hard you try. Unless you try really, really hard. So the bonds between atoms in an insulator are made of covalent bonds. And so structures like this are things like glass and diamond and charcoal. Now these bonds hold electrons in place very tightly, and that means that the electrons can't move and the substance can't conduct electricity. You can learn more about that in chemistry. Now conductors are materials like metals, which do conduct electricity. So the bonds between atoms in a conductor are caused by ionic bonding in some cases. So this is the case for salts like sodium chloride. And these bonds do allow electrons to flow freely. And so this means that the substance is able to conduct electricity. Now the lattice of a conductor is made out of positive metal ions, which are represented by these big blue pluses in the diagram. They represent the nucleus of an atom. Now the associated electrons of each atom are called delocalized, which means that they're not associated with any particular atom. So you can see here there are lots of tiny blue electrons in this picture, but none of them are really associated with any one positive nucleus. So this means that they're free to move through the structure, almost like a sea of electrons, which means they sort of flow almost like a fluid, and that's in fact used to model the flow of electrons in some models. Now electrons in a conductor are continuously moving in random directions. So if we were to take the motions of electrons at any one moment, it might look something like this. As you can see, none of them are all moving in the same direction, they're all just moving around randomly. Under the influence of an electric field that might be caused by a battery or a power socket, the electrons favor a particular direction. So instead of all moving in random directions, there'll be just a few more moving in one direction than the other. And this is what it causes an electrical current to flow. So bear in mind that in an electrical current, it's not all electrons moving in the same direction, it's just more electrons moving in one direction than in the other directions. Now, there was a problem that confused physicists for a long time concerning electrons. So Niels Bohr, some time ago, showed that the energy of an electron in an atom is quantized. That is, it can only take on certain quantities and not in between quantities. So in the case of this diagram, the electron would jump from this big circle to this smaller circle without really going through any of the spots in between. And it can take on very specific allowed energy levels, which are the circles, and no other energy levels. So it's impossible for this electron to, example, jump halfway between the circles. And for a long time, no one could explain why this happened. It just sort of was what electrons did. Before we can talk more about that, we have to talk about being able to measure the energy of electrons in these various states though. So instead of using joules, we have to use a different unit. So it's easiest to measure the energy of electrons in electron volts, which are represented by eV, which we can see here. The conversion factor is something like 1 electron volt is 1.602 times 10 to the minus 19 joules. And that's just simply the amount of energy that an electron gains when it's accelerated through 1 volt. And so Planck's constant can also be expressed in electron volts instead of joules. The reason this is useful is because most electrons have energy on the region of 1 electron volt, 10 electron volts. And if we were measuring in joules, we'd have to say 1.6 times 10 to the minus 19, 1.6 times 10 to the minus 17, and crazy numbers like that. It's easier to work with electron volts. So, Louise Dubrow came up with a way to solve the puzzling sort of fact that electrons could only take on certain energy levels. His name looks like Broglie, it's pronounced Broy. He was a French physicist, and in 1923 he suggested that electrons acted like standing waves on a string. And every energy level of the electron corresponded to one of the modes of the standing wave. And you might not have heard too much about standing waves before, so I'll just go over them quickly as soon as that moves to the next slide. Now, if we consider a plucked string with 2 fixed points on either end, it can only vibrate in an unlimited number of ways, and these different ways are called modes. So we can see it can vibrate in the fundamental mode and just go up and down, or it can vibrate like this, have a fixed spot in the middle, and then just sort of move back and forth. You can also do that with 3 different places that are moving, or 4 or 5 or however many it wants. So each of these is a different mode of the string. Now an infinite number of modes exist, but the wavelength of each mode is very clearly defined. So you can see that this pattern could keep going on forever. You could have 1,000 different nodes on the string. But for each one, you can tell exactly how long the wavelength is going to be. So this will be 1 whole wavelength, this will be half a wavelength, this will be 1.5 wavelengths. So you can, as long as the yellow squares always stay in exactly the same position, you'll always be able to find the exact wavelength. Now, these wavelengths are like the energy levels of the electron. So an electron, like a vibrating string, can have an infinite number of modes, but every mode has a certain wavelength, and there are no other wavelengths in between that act as waves. Of course, these are only modes on a string. For an electron, it's something more like a circular wave. That looks a little like this. So we can see that, once again, we have the string vibrating back and forth around this circle, and there's only a limited number of wavelengths that go around the circle. So this is called a circular standing wave. So like a standing wave, it has an infinite number of modes. You can imagine fitting, 1,000 of these wavelengths around the circle. But each mode has a very clearly defined wavelength. Here, for example, we have 4 wavelengths going around. We can count them. So there's 1 wavelength, 2 wavelengths, 3 wavelengths, and 4 wavelengths. Now, each allowed wavelength corresponds to the energy of an electron. So we can see here a number of examples of circular standing waves. Now, electrons have an infinite number of energy levels, but an electron cannot have an amount of energy that lies in between 2 different energy levels. So we can see here, here's a standing wave with just a single wavelength. Here's a standing wave with 2 wavelengths, 1, 2. And it's impossible to have a number of wavelengths that's in between 1 and 2, because it simply wouldn't match up. It wouldn't create a standing wave. And so Dubrow proposed that this was the reason that it was impossible to have an energy level in between 2 established electron energy levels. So we can see, in fact, an animation of what these standing waves would look like. We can see here 4 different modes of a circular standing wave. So we can see in this example, there's only 1 wavelength, and it's moving back and forth across the yellow circle. Here there are two different wavelengths. And once again, we have this wavelength is vibrating back and forth, and this wavelength is vibrating back and forth. 3 and 4 are quite similar, and you can sort of see the pattern emerging as we look at patterns 3 and 4. If we look at 4, for example, we can see one wavelength over here, just sort of moving back and forth as though it were a wave on a string. And this just keeps going around the circle, of course. So you can see that there are an infinite number of different modes that it's possible to have, but each one has its own particular wavelength. And in the same way, electrons have an infinite number of modes, but each mode has its own energy, and you can't move in between those energies. So an electron is able to absorb a photon of energy to move to a different standing wave energy level. So it can move from level 1 up to level 2, or level 1 up to level 3, or level 2 up to level 3. Now the energy of the photon must be exactly the energy that the electron jumps. It can't be any amount of energy in between, because then we wouldn't end up with a whole number of wavelengths going around the circle. So then that means that not all photons can be absorbed by electrons. The only photons that this electron would be able to absorb were electrons with this amount of energy, or this amount of energy, or this amount of energy, and of course all the small amounts of energy in between. So it would be impossible, for example, for this electron to absorb a photon that had this much energy, unless it was already in a higher energy state, in which it would be able to absorb an energy with, for example, this much energy. So the fact that not all photons can be absorbed by electrons is a rather important fact, and we'll get around to the consequences of that a little later on. Well, what about losing energy? So an electron can emit a photon to move to a lower energy level. And so we can see an example here of an electron dropping from energy level 2 to energy level 1, energy level 3 to energy level 1, and from energy level 3 to level 2, and then to level 1. And the emitted photon's energy is the difference between the two energy levels of the electron. So when it's dropping from level 2 to level 1, it emits a photon with exactly this much energy. We can see that if it drops from level 3 to level 1, or from level 3 to level 2 to level 1, it'll emit a different number of photons, and those photons will be at different energies. Electrons of different energies, of course, emit electrons of different frequencies. Another interesting feature of this diagram is that these energy levels are closer together than the bottom energy levels. And we can see, in fact, that that's consistent with the energy levels contained in standing waves. A standing wave with 99 nodes is much the same as a standing wave with 100 nodes, and so these are very close together. But a standing wave with only a single pair of nodes will have only half as much energy as a standing wave with half the wavelength. This concludes the theory. So we've learned a bit about the different energy levels of electrons in atoms, and a little about how photons interact with them. Let's go on to some questions. Question 1. Electrons in all metals move around randomly all the time. Why doesn't this cause current to flow? Let's go through the options. Is it A, electrons are not charged particles? Well, we know this can't be the case because electrons are negatively charged particles. We can see this because they move in an electric field. B, the current caused by the electrons is cancelled out by the current caused by the protons. Well, this isn't really the case either. We know that the electrons in, say, a metal are fixed in a grid and don't move in an electric field, so only the electrons can be moving. B can't be the right answer. What about C? The energy levels of the electron are quantized. Well, this is true, but it doesn't explain why they don't cause a current to flow when they move around. Just because an electron's energy is quantized doesn't mean that it can't move around freely in the sea of electrons. Our last option is D. The current of an electron moving one way is cancelled out by the current of an electron moving the other way. And this is in fact the case. And the reason that this stops a current from flowing is because all the energy, all the current generated by electrons moving to, say, the right is cancelled out by an equal number of electrons moving to the left. As long as there's no electric field, then there will be equal numbers of electrons in each direction. In an electric field, of course, one of these arrows becomes a little shorter and one becomes a little longer, so there is a net flow of electrons. It is, of course, possible, if you have a good enough measurement system, to notice the tiny little back and forth charges the back and forth currents generated by the electrons, but usually that's not really much of an issue. Question 2. Which is the correct answer? Electrons can absorb photons of any frequency or specific frequencies. Well, we know that if we look at the energy levels of the electrons, they can only take on very specific energy levels. And if they absorb a photon, then all of the photon's energy is transferred to the electron. And so if it can't jump up from one energy to a different energy, it can't absorb the photon at all. So we see that our answer is that it can only absorb photons of specific frequencies. And those specific frequencies are only the ones that allow it to jump from its current energy level to another specific energy level. Well, what about emitting photons? So our question here is electrons, which is correct, electrons can emit photons of any frequency or specific frequencies. Well, once again, if we consider the energies of an electron can only jump from an allowed energy level to another allowed energy level. It can't emit any photon aside from this one here if it jumps between these two energy levels. And so we see that electrons cannot emit photons of any frequency, but only the frequencies that correspond to jumping from one energy level to another. So this is the correct answer. Question 3. An electron absorbs a photon and jumps from the ground state to an energy level 12.7 electron volts above the ground state. What frequency was the absorbed photon? You can see here that because we're using 12.7 electron volts, it's a lot easier than using joules. If we were using joules, it would be something more like 1.6 times 10 to the minus 18. So in this case, we have an electron jumping from this energy level to another energy level. And the distance that it's jumped is 12.7 electron volts. Luckily, we have a measure of Planck's constant in electron volt seconds instead of joule seconds, so we don't have to worry about converting the electron volts to joules. So the absorbed photon must have had an energy of 12.7 electron volts to cause the electron to jump that far. We can use our value for Planck's constant to work with electron volts. So using our equation E equals hf, which still works, we can find an expression for the frequency of the photon, and substituting in 12.7 electron volts for energy and our value for Planck's constant as h, we end up with this expression. Putting this into a calculator, we can find that the frequency of the photon was 3 times 10 to the 15 hertz. Question 4. An electron drops from an energy level of 12.1 electron volts above ground state to an energy level of 10.2 electron volts above ground state. So that means that it emits a photon. What wavelength is the emitted photon? So this time, instead of going all the way to the ground state, if the ground state's over here, then we're jumping from this energy level, 12.1 electron volts, to this energy level, which is, of course, 10.2 electron volts. And so the photon that we're emitting isn't going all the way from this state down to the ground state, or from the second state down to the ground state. It's actually this gap in between the two energy levels. So it's a photon of much smaller energy. So once again, we can use an old equation, E equals hc on lambda, to find the energy and the wavelength of the photon. So we can rearrange this equation to have lambda equals hc on E. We can substitute in our value for h, our value for c, and the difference between the two energy levels in order to arrive at this expression here. Of course, the 12.1 minus the 10.2 is the energy of the photon that's emitted in electron volts. So, simplifying this, we find that the photon that's emitted has a wavelength of 6.531 times 10 to the minus 7 meters. This is in fact a visual wavelength that we're able to see, and if we measure it in nanometers, we find it's 653 nanometers, which is a reddish color. Question 5. Why do we measure electron energy levels in electron volts instead of joules? Surely we're more used to joules, so it would be easier to measure that. Well, the reason for this is because if we were to measure it in joules, it would be a little harder to write everything down. So measuring electron energy levels in joules means that we're always writing times 10 to the minus 19 next to everything. And of course this gets tiring quite quickly. It also means that it's difficult to sort of understand the magnitude and the difference between two different numbers measured in joules. Whereas if we use electron volts instead of joules, then we're dealing with small familiar quantities like 7 electron volts or 12 electron volts. And of course, this is a lot easier to both comprehend and to write down. This concludes the questions. In this section, we've learned about how electrons move around in solids, as well as how they interact with photons and change energy levels.